Welcome back, and today I'm going to be looking at the Raspberry Pi Pico and how it can be used in a home-built servo. I'm going to make the servo really quite cheap. Unlike before, I'm not using sort of over-engineered parts, very cheap uh, H-bridge, and the chip I'm using, of course, is the Raspberry Pi Pico, which hasn't been around for very long. It's a sort of rival to the ESP32, but it doesn't have the Wi-Fi and the Bluetooth that the ESP32 has. There's a little bit of a shortage, I believe, at the moment of this. It's not been out very long. And the nice thing about it is we can program it in Python, and it's not pin compatible, of course, with the ESP32, but once we've just defined our pins, the program's more or less the same as we would have had on the ESP32. There's a few little changes that I'll tell you about, but other than that, it's more or less the same. It seems to run very slightly faster as well. Not enormously faster, but does seem to run a bit faster than the ESP32, which I found a bit surprising. I'm going to use cheap components for the servo, so my rotary encoder is a cheap one which I bought from China. Sells for about 10 New Zealand dollars. I was using the Yumi ones, which have gone up in price now. These ones are very good price, but when I tried to use it, I couldn't get anything out of it. And it took me a while of fiddling around with pull-up resistors and all sorts of things. So I eventually realized that although the spec says that it runs from 5 volts to 24 volts, I was running on 5 volts and it didn't seem to run at all on 5 volts. I upped the voltage to 12 volts, which was the voltage I was using for the motor, and everything sprang to life and it worked really well, just as well as the other one. So I recommend these kind of encoder seems to be good, but just be careful of the supply voltage. I had a little bit of difficulty there. The H-bridge, I've also used a very cheap one. This is one they used to be selling for $1. The L298N. They've got a reputation of being a little bit cheap and nasty, but believe me, as long as you don't overload them, and they take about 2 amps maximum current, they seem to work fine. I didn't have any problem. I'm not driving an enormous motor, so it's quite satisfactory. And if you blow one up, they're very cheap, so you can buy a handful of them. There's the pin out of these boards. So there's 2 channels, output A and B. I'm only going to use one. I'll use the output A. You put your 12 volts in there, assuming it's a 12 volt motor. There's ground, and it's got a nice regulated 5 volts, which comes out. That's quite handy. And here is channel A. So you take that jumper out and you put your PWM in there, or you could put it in B if you wanted. And then these next two pins are in 1 and in 2 like we had before, which define the forward and reverse. If in 1 is 0 and in 2 is 1, it goes in one direction, and then it's vice versa for reverse, and 0, 0 for stop if you need stop, which I'm not using. And that's about it really. There's not much else to them. Software, we need the Thorny editor, which I've discussed before. It's a free download. And MicroPython. It's a bit easier to install than the ESP32. You just hold the reset button down, this white button, and you plug in the micro USB, and it's supposed to install a little drive to your hard disk. It didn't in my case, but I think it's the university stopping it because of the antivirus and the firewall. We've got quite strict rules here. It may be that. I haven't fully investigated, but Thorny still does seem to work on it. And it creates a COM port, which I had COM port 9, and I was away. Although sometimes there's a little bit difficulty when I try to transfer software to the device, but I can run on the PC and it runs on the device at the same time. So that's quite straightforward. So the controller we're using is a PID controller. its Z transform is as follows. It's got a gain Kp, a gain Ki, and a gain Kd. That's the so this is the proportional part. That's an integral, and that's a derivative part, or difference, I should call it. We can't really call it differential. Now these are Euler type integration and differentiation, which is the simplest form. There's no reason why we can't use that. Normally we wouldn't use that for transferring analog to digital, that's to say continuous time to discrete time. Filters, we wouldn't do that, but it's fine for PID control. There's no reason why you shouldn't do that. However, differentiation or difference here is fraught with difficulties in the sense that it amplifies high frequencies and can cause vibrations at high frequencies and noise. So we should have a low-pass filter, which I'll talk about next. So we want a digital low-pass filter. In order to design a digital low-pass filter, we start with an analog low-pass filter, and we convert it into the discrete domain. So here's our continuous time transfer function, 1 over 1 plus st. We need to know what cutoff, and in this case it's a very low bandwidth loop, so I'm just going to have a cutoff of 10 Hertz. In other words, at 10 Hertz, this is radians, of course, it's plotted it on MATLAB at 62.8 radians per second. It's down minus 3 dB, and it's got a DC gain of 0 dB, which is unity, and that's a typical phase shift 0 to minus 90. So we can find the time constant is 1 over 2 pi fc, where fc is 10 Hertz. And once we've got this transfer function g of s, we convert it to the z domain using the bilinear transform. Like I said before, these are the simpler Euler forms, but this is a trapezoidal form, which is more accurate. But it's only accurate if you're sampling at least 10 times higher than, in this case, 10 Hertz. That would be 100 Hertz. But I'm going to be sampling at a kilohertz, which is way out of the way, so I don't really need to worry about the accuracy here. There's a problem of warping with the phase. You don't quite get the filter that you set off to get if you don't sample high enough, at least 10 times higher than the highest frequency of interest. Because I'm sampling 100 times higher, I really don't have that problem. So the sampling frequency is 1 kilohertz, and I can set that up with a timer loop, a timed interrupt. And therefore the sampling interval is 1 millisecond. To convert to g of z, from g of s, I substitute s equals 2 over ts, with ts as the sampling interval, z minus 1 over z plus 1. And if I do a little bit of algebra, just substituting it into this guy here, so substitute this into there, rearrange, and I get this Z transform, where KF is defined by this and AF is defined by that. So I've written it both in the so-called forward shift with plus Z and backward shift with Z to the minus 1. Z to the minus 1 is more convenient when we're finding the difference equation. So in discrete systems, we have difference equations. In continuous time analog systems, we have differential equations. Difference equations are great. We can use them and put them into software, and I'll show you how to do that in a minute. But you can see this thing KF, it's like a gain. It's a function of TS, the sampling interval, and T, that's the time constant of the filter, and AF is given by this here. If we go back to here for g of z, we can easily deduce the difference equation. And this says that the output at present time k is minus AF, where AF is defined here, times the previous output plus this constant KF times the input u of k plus it's the previous time it happened, the previous loop around. So u at time k plus u k minus 1. That's the best way to write that. And without more ado, have a quick look at the software, and it's standard MicroPython we need math. That's just for the pi thing. I'm using pi. If you just use 3.14, don't suppose you'd really need that. You can do away with it, but I'm using that for the filter, so that's why I've got that. I need pin to define the pins, PWM, and a timer for the timer interrupt. I defined the pins for the motor encoder. It's coming out the back of the DC motor. It's pins 2 and 3. I'm just doing them, consecutively. And then for the set point encoder, that's the new one I bought, which is quite cheap, pins 4 and 5. And then I need in 1 and in 2 for the H bridge to forward and reverse. It's pins 6 and 7. And then I create a PWM object on pin 8. So the PWM is coming out of pin 8, and it's going to go at 50 Hertz. I also use pin 9. I've commented the part out, but that's just to monitor the sampling frequency that the loop runs at to make sure that it's running at the right frequency. If I'm designing a digital filter that runs at 1 kilohertz, it has to run at 1 kilohertz. If I run it at say 500 hertz or 50 hertz, everything would be, the time constant would be all messed up. It wouldn't behave the way it's supposed to behave. So it must execute at the right in the right time. So I set up a timer. It's a hardware timer interrupt, and this is how it's done in the Raspberry Pi. It's very similar to the ESP32. The only difference is the time isn't actually defined. The frequency is, in this case, 1 kilohertz. It can't really go, I think might be able to stretch 2 kilohertz, but I can't go much higher than that. It's not that fast really, like running in Python anyway. It's periodic. It's got to run, again and again, and that's it really. That's my timer. And then within it, I've got this thing called interrupt counter, which I increment, and then I have a check. If the increment counter is say 1, then I do the loop. If it's not, I wait. And it's actually very accurate way of doing it. It's there are other ways, of course, but this hasn't got a real-time operating system, so you'd have to do everything. Now we've got interrupts for the motor encoder and for the set point encoder. So this is the actual interrupt. It goes on pin B, encoder pin B. That's defined up here. Encoder pin A is pin 4, encoder pin B, pin 5. So on pin B, it says if there's an interrupt on the that's actually on the falling edge, but it could be on the rising edge. It doesn't really make much difference. I did have it on I think when I was experimenting, because I couldn't get the encoder to work, I had it on, normally have it on the rising edge, but that works all right as well. And the handler is, the handler for the motor is here, and this is a little like a subroutine. It's a function, and this is the object, which I call pin_m for motor. I don't really need that as such, but again, when you're experimenting with it, you can print out the count as it's going along, although that would slow things down, so you don't really want to do that. But when you're testing it, it's handy. And it just says the count and the object that triggered the motor handler, it's when there's a trigger on the falling edge, it jumps to this routine and it increments the motor, okay, irrespective of what else it's doing in its infinite loop, which comes later. So we do the same for the set point. It's a counter for the set point, which is 0, and we have a handler for the set point, and we trigger on the falling edge. In this case, rather was the leading edge, but it doesn't really make any difference as far as I can see. And then we have a function to work out the low-pass filter. So the sampling interval is 1 milliseconds. The cutoff frequency is 10 hertz, and I've just defined this function called low pass, which takes in TS and FC, and there's a semicolon. Everything must be aligned in a block here. I'll throw up errors, work out the time constant of the filter, and then it works out this thing called KF, which I showed you earlier. Let's just go back to that. Here it is, and AF. And then something you might not know unless you know Python is that we put the two values into, it's called a list. It's like an array. It's not quite an array because I don't think you can divide by or multiply them like you can in an array easily. But it's called a list. And so we put them, I'll just call it values, and then it's return the values. And then the values 0 and 1. So I just put them into the thing KF and AF is values 0, values 1, like an array. And then we come to the difference equation. Well, that's set up for later. We'll see in a minute. Interrupt counter is 0, and these are all just initializations to 0. These are the gains I use. I couldn't put much integral action on, otherwise I end up with instability. It's already got an integrator in the form of a mechanical integrator because it is a position servo, but it's always good to have another integrator if we can. So you've got two integrators, but it's just a very light integrator. You end up with too much overshoot otherwise. So the main loop is here, so it loops forever while 1, or you can have while true. If the interrupt count is greater than 0, it subtracts 1 and it goes to 0, and then it gets incremented again by the service routine, the timer service routine in the timer interrupt. Save the old value of the error, and then the new error is the set point counter minus the motor counter. And we need to reverse the motor if the error is in the wrong direction. So again, you may have to swap these values around in 1 and in 2 to get, you must have negative feedback, otherwise it'll start running off and won't be any good. The proportional term is just the error times KP. The derivative term is the error minus the previous error times the gain, which is the KD. That's the proportional, the differential gain. And then the integral old equals integral new. That's one way to do it. There's a simpler way, but anyway, that way will work. And I've got the new value of the the new value of the integrator output is, and ignore that for the moment, is the old value plus the error times the integral constant. Now the reason I've got 0.999 is I'm actually integrating what's called a leaky integrator. It hasn't got minus 90 degrees phase shift at sort of low at DC. It's more like kind of a phase lag compensator, but it's very close to an ideal integrator. That's why it's not quite so severe, and it prevents any oscillations or running off of the motor. Anyway, I find it's a good thing. You can actually run without it, but it's so it's got a leaky integrator. Use it in digital signal processing. Why not use it in control? Then the PID is the derivative term plus the integral term plus the the proportional term plus the derivative term plus the integral term. Now for the low pass filter. Remind ourselves that's the difference equation. So you want the minus AF times the previous value. So there's y is equal to minus AF times, and the y1 here is the previous value because I've stored the previous output here. Y1 equals y plus KF, which we worked out earlier, times U plus U1, and U1 is the previous input. So we've got stored that as well. U1 equals U, and U is the input to the filter, which is the output of the PID controller. And that's it really. Of course, you need to tune it. You must run round this loop at 1 millisecond if you've designed the sampling frequency at 1 kilohertz. Otherwise, this low pass filter will not perform the way it's supposed to. Then we send the output to the PWM, which must be an integer form. It's got to be absolute. If it's negative, it's got to be swapped. If you're wondering about what happens when it is negative, well, this bit here it changes the sign of the error by swapping in 1 and in 2 in the hardware, so that's taken care of. This bit at the end I've commented out was what I've used before for checking that the sampling rate is indeed, or this loop in fact, runs at 1 milliseconds by just sending a logic level 1 and then 0, 1, 0 alternatively to a pin. I think it's pin 9 in this case. So if the sample pin is, if the sample pin value is true, and that's what that means. If sample pin value, that means true, then it becomes false, it becomes 0, else it becomes true. So it just goes 1, 0, 1, it just toggles. There doesn't seem to be a toggle command in this particular version of Python for this machine that I'm aware of, but if there was, of course, we could write one if we wanted to, but because I only use it once and then comment it out, there's no need to do it again. So that's how we do a controller. You see, it's not particularly big. Thing to watch out for is the PID terms here in the infinite loop and the filter afterwards. You can run it without the filter, and then you don't have to worry so much about the timing of the loop. You could even run it at whatever speed it happens to be at. But if you then add anything else to it, you'll change the timing. So it's good to have it timed using a timer interrupt. It's really good practice to do that. So that about takes care of it, and we'll just go on to the demo, and you'll see how the performance is. That's it. So this is the setup. This is the quadriger incremental encoder. This is the Raspberry Pi Pico. This is an H-bridge, and that's actually this very cheap L298N one, deliberately chosen. It takes about 2 amps. It's just to make it a cheaper setup. And the motor is a little bit expensive. It's about $40, but that's New Zealand dollars, I think. But you can get cheaper motors. You don't have to use this as long as it's got an incremental encoder on the back. And I've set it up so that I can turn the power off. Here is 12 volts. It boots up automatically. And there it is. And it's actually quite stronger than it looks, this thing. It may not look like much, but if I put this in here and I can turn it around, you can see it lifts. It's quite heavy. It can do a bit of damage. So as a servo, it's quite strong. It's quite a neat and cheap way to make a servo.